video, we're going to be looking at derivatives. And I bolded derivatives because anytime anyone mentions calculus, the first thing that probably comes to their mind is the concept of derivatives. And that's for a good reason, because derivatives are really important in calculus, but also in the real world for real world calculations. And it's important that we get a foundational understanding of what derivatives are. So, the first kind of concept I want to go over is average rate of change. Now, most of you guys probably know average rate of change as slope. So how do we find slope? Well, our basic algebra class told us that slope is delta y over delta x. Or, if you want to write it out, y2 minus y1 over x2 minus x1. And from this graph over here, I just wanted to show that you can actually write this as, let's say we wanted to find the slope between this point and this point. So if we drew a line intersecting them like that, well, we would just apply the slope formula and we'd do y2, which is f of b, minus y1, which is f of a. So f of b minus f of a all over x2 minus x1, b minus a. And so that's the basic idea of what a slope is. Now, what derivatives are is they tell us the slope at a singular point. That's why they're super important and special. They give us the slope at a singular point. So let's say we wanted to find the slope at this point here. Why don't we give, whoops, why don't we give this another name? We'll just call it x. And we'll say that this point over here, b, is x plus h, where h is just this distance right here. And instead of calling this f of b, why don't we call this f of x plus h, and then this would just be f of x. So if we wanted to, the basic idea is, why don't we bring this point closer and closer to this point right here. And if you look at what's happening, we get these secant lines until eventually we get until eventually we get really close. We want to get really close, and we get a tangent line at that point. Now, the previous videos, what did we learn that would give us, or where we could get really close to that point? Limits. And all we have to do is take the limit as our distance between these 2 points. So the limit as h approaches 0, so that the distance becomes essentially 0. And we get this tangent line at that point. So if we take the limit as h approaches 0, well, what are we taking the limit of? Well, we're taking the limit of the slope, basically. And so what's our formula for the slope? Well, we know that it's f of x plus h minus f of x all over the distance between them, x plus h minus x, which just becomes h. And there you have it. This is a derivative. And it gives us the slope at a singular point. And the derivative is also, you can also name it as the instantaneous rate of change rather than the average rate of change, because it's the instantaneous rate of change at a singular point. Okay, so I want to go over some examples real fast. Just some quick examples to kind of better implant this idea in your head. So let's take a look at an example. We have f of x equals x squared. And first part of this problem is find the average rate of change. And from now on, I'll abbreviate rate of change with ROC. On the interval, the closed interval, -1 to 3. Okay, well, we know the formula for the average rate of change. It's just f of b minus f of a all over b minus a. So we plug in what we know. If we want to do we can then write this as f of 3 minus f of -1 all over 3 minus a -1. Well, what's f of 3? If we plug in 3, that's 9. If we plug in a -1 to find f of -1, that's just 1. And then bottom becomes 4. So then we get 8 over 4, which is equal to 2. So that's the average rate of change on that interval. Now, the second problem I want to go over is finding the derivative or instantaneous rate of change. For the same function. So we just learned our formula for the derivative, which is the limit as h approaches 0 of x plus h minus f of x all over h. And I know if you've been introduced to the idea of derivatives before, maybe in a physics class, a calculus-based physics class, you know that there are some tricks and shortcuts. I promise we'll get to those later on, but this is foundational to the idea of what derivatives actually are. So stay with me until we get to those tricks. So continuing on, let's go ahead and plug in what we know. So we know that our f of x plus h would just be x plus h squared. We know that our f of x is x squared, and we know that our h is just h. Now, if we wanted to plug in 0 here for h, you would see that we'd run into some problems in that we'd get 0 over 0. And we learned before that that's an indeterminate form, and we need to do some sort of manipulation to get this all cleaned up. And the trick to doing that is just expanding this out. So we'll just expand that. It'd be x squared plus 2xh plus h squared minus x squared all over h. That's what we have, and obviously we still have the limit here. And so so now you can notice that these x squareds actually go away, and then we're left with the limit as h approaches 0 of 2x plus h. Oh, sorry, not 2x plus h. 2xh plus h squared over h. So then on the top, we can't plug in 0 yet because we still get 0 over 0. We need to factor out that h on the top. So we get 2h, we get 2x plus h. And then you notice that these h will go around. Sorry, there's supposed to be a limit in there, but you get the idea. And we're left with the limit as h approaches 0 of 2x plus h. Finally, we can plug in 0 for h, and we get 2x. Now, this is really, really cool because this 2x will give us this slope. It's a slope formula for the slope at any point. And that's just amazing to think about. You can plug in any value of x and get the slope at that point using just that formula. So it's interesting. And so for the final part of this video, I want to take a look at this problem where it's find the equation of the tangent line at x equals 3 for the function y equals x squared. So same function. And now before I mentioned that tangent lines actually give us the slope at that point, because tangent lines touch touch the function at that point, only at that point. And so if we know the slope of the tangent line, that'll give us the slope at the point. So that's the basic idea. So to take a look at this To find the equation of the tangent line at x equals 3, we're going to want to use this form of the point slope form for the equation of a line. And we know from the previous problem that if we plug in 3 to 2x, we'll get the slope at that point. That'll give us our m. So if we get m is equal to 2 times 3, so m is equal to 6. So we are left with 6x minus x1. Now we got to find out our x1 and our y1. Well, that's pretty simple because we're given x1 already, which is 3. And we can find the y value just by plugging into our original function, so that would give us 9. So we're left with y minus 9 is equal to 6 times x minus 3. And you could leave it like that. That'll be fine on an AP test, on a test, usually because you have the answer right. I mean, you can do some simplification, but that's just basically the correct answer. And so that's going to wrap up this video.